Hi, everyone. Welcome to today's Learn and Share session. We are very happy to have Wilson and Nguyen presenting Mangrove. Wilson is from Stanford University and has been working on folding SNARKs for a while now. He has contributed in very interesting papers, including revisiting the Nova proof system and accumulation without homomorphism. And today we have him presenting Mangrove, a scalable framework for folding-based SNARKs. So I hope you enjoy, and thanks a lot, Wilson, for being here.
Cool. Thank you for inviting me. So today I'll present Mangrove, which is our new scalable framework for constructing folding-based SNARKs. This is joint work with my co-authors from Stanford. So let's recap on what a SNARK is. Well, informally, it's a method to efficiently prove the outcome of some computation. More concretely, we'll consider an arbitrary arithmetic circuit C and a public instance X. The claim is that there exists some witness W, which indeed satisfies the circuit. In particular, the circuit, when evaluated on these inputs, evaluates to 0. It consists of a collection of algorithms, in particular, a setup procedure, which takes in the security parameter and outputs a structured reference string. In a pre-processing step, this structured reference string, as well as a description of the arithmetic circuit, outputs a proving key and succinct verification key. Now the prover will output a succinct proof, pi, for which the verifier, along with the succinct verification key, public instance, and this succinct proof, will check it and output accept or reject. They satisfy several key properties, in particular, the usual notions of completeness, knowledge soundness, succinctness, and optionally zero knowledge. In particular, completeness states that for all honest provers, the verifier should accept. Knowledge soundness states that for all malicious provers, there should exist a corresponding extractor, which if the malicious prover convinces the verifier, the extractor should be able to succeed in extracting a witness that satisfies the circuit. Succinctness means that the proof is small, in particular sublinear in the size of the circuit, and the verifier runs in time polynomial in the public instance, and also sublinear in the overall circuit size. I would like to reference a quote from a seminal work in 1991, in which the author stated that a SNARK should allow a single reliable PC to monitor the operation of a herd of supercomputers. Now, while over the past several decades, since 1991, we've made significant improvement, in particular concrete improvements to the performance of SNARKs, we're still a long ways from actualizing this dream. In particular, to do so, we would have to prove circuits of incredible size. So, where do existing modern constructions of efficient SNARKs fall short of realizing this dream? Well, I'll classify these existing concrete SNARKs as monolithic SNARKs, in particular SNARKs that operate over the circuit as a whole. They require that the prover memory is linear in the circuit description. They oftentimes require a trusted setup, which produces a linear size structured reference string. Now, for circuits of very huge size, linear prover memory, as well as a trusted setup, limits the amount of parties that can actually participate in such setup or proving procedure. And hence, they provide barriers to proving very, very large circuits. However, there have been existing works that produce more efficient provers, but the issue is that they require clusters to actually be concretely efficient. There are also streaming SNARKs, which do not suffer from this linear prover memory, but indeed have trusted setup and linear size structured reference strings. And most importantly, their provers are asymptotically and concretely slow when compared to these other monolithic SNARKs. So, is all hope lost? Well, there also exists another class of SNARKs called incremental SNARKs. So these are the usual notions of incremental verifiable computation or proof carrying data. These incremental SNARKs suffer from none of the drawbacks of monolithic SNARKs. However, there is a huge caveat. In particular, they're only concretely efficient for very repetitive or uniform circuits. So what do I mean by a repetitive or uniform circuit? Simply that the overall circuit consists, simply that the circuit consists of the same subcircuit repeated multiple times. In particular, they're just the same subcircuit, just connected to each other, all the way leading to a single circuit output. So to illustrate the issue with attempting to use incremental SNARKs when trying to prove arbitrary circuits, consider the following uniform or repetitive circuit, right? In particular, I've just enlarged this image. Incremental SNARKs operate by proving each repetitive subcircuit, the exact same circuit, one by one, recursively, all the way till the final output. However, when we consider arbitrary circuits, this arbitrary circuit consists of many distinct subcircuits, as well as arbitrary wiring requirements within the circuit. And hence, applying the same strategy that incremental SNARKs normally do would not apply. In particular, it's really hard to partition just arbitrary circuits into a series of identical subcircuits. So if only there was some way that we could benefit from incremental SNARKs while being able to handle arbitrary circuits as other monolithic SNARKs do. And that's exactly what we do. And hence, we are able to recover all the benefits of incremental SNARKs. So in Mangrove, we introduce several new techniques which allow us to do so. We introduce a uniformizing compiler, which is able to reduce the satisfaction of an arbitrary circuit to a sequence of identical steps, for which we can readily apply incremental SNARKs, particular proof carrying data or IVC, to prove. However, there is a major caveat with immediately using the uniformizing compiler. It's that each of these steps contains a pretty expensive cryptographic operation, which would make this strategy practically infeasible. However, by simply inspecting each of these steps and treating them as a member of a polynomial relation, which we'll discuss further, we'll be able to avoid this expensive cryptographic operation and be able to recover an efficient SNARK. Finally, we introduce folding schemes for polynomial relations. In particular, we're able to reduce the task of proving many of these identical steps to the task of proving a single step. Now we can readily apply incremental SNARKs to repeatedly execute these folding schemes, and we're able to recover our overall Mangrove SNARK. So, what do these techniques actually get us? Well, by applying these tricks and techniques, plus existing incremental SNARKs, we're able to obtain the Mangrove SNARK, a SNARK that has a constant size, transparent common reference string. So in particular, we do not require a trusted setup. It maintains a linear proving time, in particular, a linear number of field and group operations. It requires only constant prover memory. It can be viewed as a streaming algorithm, which only takes 2 passes over the input data. It's readily parallelizable and hence readily distributed. And also, most importantly, has great concrete performance, which I'll discuss a little further at the end. So, how does this uniformizing compiler work? Well, let's take a detour into our interpretation of Planckish arithmetization. This was introduced by the Planck paper in 2019. In particular, let's consider this arbitrary circuit here, which has pin values, which are field elements, and also wiring constraints. Here I denoted the wiring constraints as different colors. In particular, we would want W1 to equal to W5 and W6, W7 equal to W8, and so on and so forth. Let's see how we can somehow encode this arithmetic circuit as concrete vectors. In particular, here I've laid out all of the gates one by one. We can encode the type of gate using a selector vector, in particular 1 for a multiplication gate or 0 for an addition gate. Furthermore, I've laid out all the pin values as this vector z, which I'll refer to as the extended witness vector. In particular, consists of the instance and also the extended witness. Now, if the selector vector is 1, we would expect that the corresponding tuple satisfies a multiplication constraint, while if it's the selector value is 0, we would expect the corresponding tuple to satisfy an addition constraint. Okay, but how do we actually encode these sort of copy constraints or these sort of wiring within the arbitrary circuit? Well, the Planck paper made a key insight that when you want to check that W1 is equal to W5 equals W6, it suffices to actually check a cyclic permutation is equal to itself. In particular, notice I have a tuple here with the 3 pin values, and all I've done is applied a cyclic permutation. Now, it turns out that checking that this tuple is equal to this tuple suffices to check that they're all equal to each other. In particular, we apply a cyclic permutation here. And furthermore, to check that these pin values are equal to each other, similarly, we just check a cyclic permutation. And also, furthermore, we check another cyclic permutation. So in order to check that the extended witness vector satisfies all these sort of copy constraints or these wiring constraints, we simply have to check that the extended witness vector is equal to this following permutation of itself, particularly that z is equal to a permutation of z. Here, the permutation just consists of each of the cyclic permutations composed of each other. So what we've done is we reduced these sort of copy constraints to simply just a permutation check, to checking that this extended witness vector is equal to a permutation of itself. So one example of a concrete encoding of a permutation is simply just the permutation of the corresponding indices. So here I just have an index counter, which counts from 1 to 12. And by applying the permutation, we now have a concrete representation of the permutation vector. In particular, all we've done is just permuted these indices. Okay, so in total, what is the Planckish randomization? So here I've just stacked all of the corresponding vectors on top of each other and segmented them into 4 different chunks. The number of chunks here is just arbitrary. The Planckish circuit encoding, in particular, consists of just a selector vector and a permutation vector, as well as a corresponding gate polynomial, which checks the sort of addition or multiplication constraints. For those who are more familiar with Planckish randomization, this can also just cover any custom gates. So this extended witness vector satisfies the Planckish randomization if and only if z is equal to a permutation of itself. So these are to handle the copy constraints, but also that the gate checks are satisfied. In particular, for every selector chunk, the gate polynomial, when evaluated on the respective chunk of the extended witness vector, evaluates to 0. So this will simply just check the multiplication or addition constraints. Now, if we look at the Planckish circuit encoding, it seems to already have a very uniform structure, which may suggest that maybe we can just partition these vectors and then immediately obtain something we can apply an incremental SNARK to. However, there are a couple barriers. But first off, let's consider the gate checks, right? So here I've simply just partitioned the extended witness vector and the selector vector into distinct chunks. Of course, these chunks are arbitrary. You could consider where it spans 2 chunks or 3 chunks or 4 chunks. Checking each of the gate polynomials equal to 0 is independent of every other chunk. And so we can just do this one by one, going down the extended witness and selector vector. So gate checks don't actually provide a barrier to viewing this as a uniform computation. However, the real issue is when we deal with copy constraints. In particular, if we try to apply a similar strategy of partitioning this extended witness vector, checking the permutation check or checking the copy constraints would require very non-local checks. In particular, we would have to check some wire value or some pin value is equal to another pin value way off into the other side of the extended witness vector. So going one by one won't allow us to actually recover a very repetitive circuit that checked copy constraints. So if only there was a way that we could just check these somehow global copy constraints, but only by doing a computation that is like chunk by chunk, particular independent of the other chunks. Well, the Planck paper has this beautiful theorem, which it's in the appendix. In particular, let Z and the permutation vector just be some vectors of field elements, in particular, where the permutation vector actually encodes a permutation. Then Z is equal to a permutation of itself, if and only if the following products are equal as polynomials. In particular, we can notice that a product has a very, very local or repetitive structure. In particular, it ends up being, each step of the product ends up being independent of the rest of the steps. Particularly, we don't have to gather local values, global values. So let's see how we can recover sort of a uniform or repetitive set of checks just from this sort of permutation argument. Well, let's query this identity over a random alpha beta. Now, this reduces to a concrete product. In particular, we have to check that 1 is equal to the following product. The key insight is that we can arbitrarily partition this product. In particular, if this product is over n elements, why don't I just do 5 elements, 5 elements, 5 elements, and so on until I obtain the overall grand product. So we can just partition the product into a series of local products, which I'll denote by P1 through PC to denote C chunks. Now, all we have to do is calculate this local product 1 by 1, and also calculate the overall grand product by multiplying P1 by P2 by P3 all the way to the end, and checking that the overall grand product is equal to 1. So now we have enough to discuss how the uniform compiler operates. In particular, here we have the arbitrary circuit as before. In a pre-processing step, we'll actually commit to chunks of the Planck circuit encoding. So here what I've done is I've chunked up the Planck circuit encoding, which consists of the selector vectors, the permutation vector, etc. And I've also chunked up the extended witness vector. So now in a pre-processing step, the verification key simply just consists of a streaming-friendly commitment to each of these chunks. In particular, you can consider like a Merkle tree or a Merkle-Damgard hash. In the first step, the prover similarly commits to its extended witness vector using a streaming-friendly commitment. The verifier will reply back with the random challenges we stated before. And now, this is literally the uniform compiler. In particular, by introducing one more round here, we've effectively reduced the satisfaction of this arbitrary circuit to just a series of repetitive checks. In particular, all that remains is that the prover will just send over the candidate's Planck circuit encoding, as well as the extended witness vector, and the verifier just has to perform the following checks. So here, F is simply just a polynomial map. You can think of this as just a multivariate map, which consists of just a bunch of multivariate polynomials for each index of the vector. Now, this polynomial map will simply just calculate the gate check that corresponds to that particular chunk, as well as just computes the partial product. So for all the chunks, we just check that this polynomial map evaluates to 0. Furthermore, we have to make sure that for each of these partial products, if we take the grand product over them, it's equal to 1. And also, we'll have to recompute the commitments to the circuit encoding, as well as the extended witness vector, and check that they do indeed align with what we saw in pre-processing, as well as aligns with the commitment that we saw in the prover's first message. Now, this is already a series of repetitive checks. However, the issue here is that sending these vectors naively, right, incurs linear communication. In particular, the circuit encoding is just the size of the overall circuit, and the extended witness vector is the size of the instance plus the witness. So by itself, this here does not actually recover a SNARK, but instead recovers a NARK. So basically a non-interactive argument of knowledge that is not succinct. However, as illustrated before, these set of checks are incredibly uniform. In particular, it's just very repetitive checks. So we might actually be able to apply an incremental SNARK, so IVC or proof carrying data, to actually just prove knowledge of this corresponding message that satisfies these checks, instead of actually just sending these vectors in the clear. So let's see a first attempt at constructing a SNARK. So the goal is to construct a repetitive circuit such that it takes in as input these corresponding chunks and outputs the overall commitments to the Polygon circuit encoding, the extended witness vector, as well as computes the overall grand product. Okay. Also additionally checks that the polynomial maps evaluate to 0. So this is just a repetitive circuit. So what does this repetitive circuit look like? Well, it consists of a bunch of subcircuits just repeated over and over and over again in a tree-like manner. So in the base case, we check that the polynomial map evaluates to 0 on the corresponding chunk input, as well as we compute a subcommitment to each chunk. In particular, like we'll produce a subcommitment to a chunk of the Polygon circuit encoding, as well as a chunk of the extended witness vector. And then in the recursive case, in particular, the recursive subcircuit, we'll just simply recursively compute a Merkle tree over these subcommitments, as well as recursively compute the overall grand product. So in particular, if we take in L input nodes, so this is like overall, this is just a tree which has L arity. We just compute a hash over the subcommitments and also just take a product of all the products we've seen so far. And so eventually, at the very top node, we'll eventually just compute the overall commitment to the Polygon circuit encoding, the extended witness vector, and also the overall grand product. So what goes wrong now if we just use an incremental SNARK to prove this repetitive circuit? Well, it turns out that we'll actually obtain a SNARK that meets all of our asymptotic requirements. However, it would be completely infeasible to run this SNARK in practice. In particular, representing the commitment or the subcommitments to each chunk would be incredibly expensive. In particular, we would have to represent the commitment algorithm as a concrete circuit. So imagine doing a hash for every single field element in the chunk, or doing a Peterson commitment for every single element in the chunk. So it turns out that this will have like hundreds to thousands of times overhead over our ultimate final solution. And so in fact, we're not going to do this because this would be incredibly inefficient. Instead, maybe we'll find some way that we can actually avoid doing this commitment operation and replace it with a much cheaper operation. So let's see if we can somehow avoid this expensive commitment operation. Well, in order to actually discuss what we replace it with, I'll have to take a brief detour or review of folding schemes. In particular, the task of a folding scheme is to reduce the task of proving L statements to the task of proving a single one. So what does that end up looking like? Here I have a folding prover and a folding verifier. The folding prover will take L instance witness pairs of a relation, and the verifier will simply only take the corresponding L instances. After some interactive protocol, the folding prover will take its original inputs as well as the transcript and output a single witness. Correspondingly, the folding verifier will just output a single instance X. Now, at some later point, the prover can send over this witness, and the folding verifier simply just has to check that this instance witness pair belongs to the original relation. Now, what are the key properties that a folding scheme must satisfy? In particular, if we view the folding prover plus this additional last message as an argument prover for the relation repeated L times, and we view this folding verifier plus this final check, some people refer to this final check as the decider, these can both be viewed as a prover and a verifier for the argument for the repeated L relation. In particular, this will end up just being a complete and knowledge sound argument for the relation where we repeat it L times. So the issue with folding schemes is that in order to represent these sort of schemes or algorithms in a circuit, we'll actually have to have an explicit description. In particular, we won't be able to just obtain an argument in the random oracle model and use this in a circuit. So what we'll have to do is somehow obtain a folding scheme in the standard model. So what we can do is apply fiat Shamir to this interactive protocol to produce a non-interactive folding scheme. So first, now instead of interacting, the folding prover will just simply output a witness W and a folding proof pi. And the folding verifier will take in this folding proof pi and also output a single instance X. However, this is in the random oracle model, so we can't represent it as a concrete circuit. So we'll apply a heuristic assumption. In particular, all prior works on incrementally verifiable computation, as well as recursive SNARKs and proof-carrying data, all make this heuristic assumption. In particular, by instantiating an argument in the random oracle model with a concrete hash function, so replacing a random oracle with a concrete hash function, they assume that they'll still maintain a knowledge sound argument. And so we'll just simply replace this random oracle with a concrete hash function, and now we'll obtain a folding prover and a folding verifier that could be represented concretely as a circuit. So what we'll end up actually doing is replacing this commitment procedure with just a cheap folding verifier. So instead of the following repetitive circuit, which takes in just the chunks of these vectors, recomputes the commitments as well as the overall grand product, we'll instead have a repetitive circuit that takes in commitments to each of these chunks and then just computes the same exact overall commitments and also partial product. But now we have an additional folded instance X for which the prover can finally provide a witness. And so in particular, we'll be able to move the commitment operation to outside the recursive repetitive circuit. So what do these instances actually look like? Well, let L be some linearly homomorphic commitment. You can think of a Peterson commitment, for example. Additionally, the repetition of a Peterson commitment is also just a linearly homomorphic commitment. So here, instead of the inputs to the circuits being these chunks, instead is a linearly homomorphic commitment to the chunks, and now the witness values are simply just the chunks themselves. The requirement of this relation is that the polynomial map will evaluate to 0, as well as the instance being the linearly homomorphic commitment to the witness. And so now, instead of having this expensive commitment operation, we'll instead add to the recursive case a folding verifier. And now, in the base case, we don't do a full commitment to a subcommitment. Instead, we just do a constant number of hashes. In particular, we just check that one field element is equal. We take a hash of a single commitment. So you can imagine this being a group element. So a single hash of a group element and another hash of a single group element. So now the overall repetitive circuit will actually be independent of each chunk size. So the recursive overhead will end up being independent of the size of the vectors. And so we can just choose the size of vectors which meet our particular memory requirement or optimize our proving speed. So indeed, with this repetitive circuit, it's completely feasible and actually incredibly efficient just to apply an incremental SNARK to prove this procedure. In particular, all we need to do is just compute a bunch of folding verifiers, calculate some products, and calculate a Merkle tree over the inputs. So it's very, very cheap. So what is actually this computation at the nodes? So I briefly illuminated that this instance is simply just a commitment, and the witness is just the raw vector. However, it satisfies other requirements in particular. So what we saw before, the instance is just a linear homomorphic commitment to the witness, which is just a vector. We required that the polynomial map F evaluates to 0, and also that this commitment relation actually holds up. Well, we can view this more abstractly as the following relation. In particular, the witness is just a vector over the field. The instance is just any linearly homomorphic commitment of the witness. And also just that you have any arbitrary polynomial map F, and that the polynomial map F evaluates to 0 on the witness. Now, the issue with this sort of relation is that we won't actually be able to design a folding scheme for it. So we actually have to consider a generalization, which instead of checking that the polynomial map evaluates 0, we'll have to actually handle arbitrary evaluations In particular, instead of checking that the polynomial map evaluates 0, we'll actually check that the commitment to this evaluation is equal to a commitment in the instance. So now the instance consists of two commitments, one to the witness vector, but also a commitment to the evaluation or the claimed evaluation. And it turns out that this sort of polynomial relation will actually be able to design a folding scheme for it. And also, in particular, this polynomial relation will actually be general enough to capture a lot of the other existing schemes. So for example, like hypernova or protostar. And so indeed, this is a pretty powerful generalization of existing sort of relations that folding schemes fold. So how can we actually construct a folding scheme for these polynomial relations? First off, I just want to say that folding schemes by themselves are a pretty active area of research. In particular, in the last couple of years, we've seen a Cambrian explosions of works, all starting from the original BCLMS paper, which introduced accumulation schemes, but also really took off when NOVA occurred. So NOVA introduced the first folding scheme for committed relaxed RNCS. And since then, there have been made consistent improvements to the efficiency of these folding schemes. But the issue is that we need folding schemes in particular for polynomial relations, not the exact relations that were provided in these prior works. And what's interesting is that by designing a folding scheme for polynomial relations, we'll actually be able to recover a lot of these prior works. So indeed, it is a sort of generalization. So in order to discuss or construct a folding scheme for polynomial relations, we'll actually have to go over some background. So the construction I present here will actually be a generalization building upon recent work, particularly accumulation without homomorphism, and also the protogalaxy work. The issue is that these specify very restricted structures, but we'll need ones for polynomial relations. In particular, we'll need it just to hold for arbitrary linear maps. So I'll try to more generalize these prior constructions. So let H be a subset of the field. In particular, you can consider any arbitrary subset that just has L inputs. You can imagine just 1, 2, 3, 4, all the way to L. V is the corresponding vanishing polynomial for the set. In particular, it's the polynomial of least degree that just vanishes on every point in this subset. Furthermore, we'll let L1 through LL denote the corresponding Lagrange basis for this set. We'll need the following theorem to actually prove, we'll need the following theorem to actually discuss how the folding prover operates. In particular, let F be any arbitrary polynomial map of degree D. You can imagine this being like some RNCS relation or CCS relation. For all x1 through xl, so these are simply just vectors over the field, there exist corresponding vectors q such that the following expression holds over indeterminate y. Now, at first glance, this may seem pretty opaque, but we'll break it down into its individual components. In particular, what we've done here is we evaluated the polynomial map on another polynomial map of the xi's. In particular, we can see that this individual polynomial evaluates to xi on every hi. So when we evaluate on h1, for example, this overall expression will evaluate to f of x1. Similarly, here, we can see that this expression here will evaluate to f of xi on hi. And so when we consider h1 through h2 all the way to hl, this whole entire expression on the left side will actually just vanish on every point in h. And hence, we'll actually be able to derive these coefficients simply by just dividing by the vanishing polynomial repeatedly for every index of the polynomial map. And so these qj's will simply just be the coefficients of the corresponding quotient polynomials. So now we have enough to actually discuss how we can concretely construct these folding schemes. In particular, we'll derive the vectors q0 through q dl minus 1 minus l, which in particular are just the coefficients of the quotient polynomials. We'll send over commitments, linearly homomorphic commitments, to these quotient coefficients. The folding verifier will send back just a random field element R. And now the folding prover will simply just output the corresponding random linear combination of its witness inputs, in particular just the evaluation of that polynomial. And the folding verifier will similarly just take a random linear combination of the corresponding input commitments. And now the folding prover will simply just send over this corresponding instance, and we'll just check that the instance witness pair belongs to the original polynomial relation. So now what we've done is we've actually just constructed a folding scheme for polynomial relations, and now we can actually concretely put this folding verifier into our repetitive circuit. So what's the analysis of this protocol? Well, let's define the maps as before. And remember, we just described how to construct an argument for the polynomial relation from the folding prover and folding verifier as before. It turns out that if you take the fiat Shamir of this argument, you'll end up recovering a non-interactive argument in the random oracle model for the polynomial relation repeated L times. So this is what we stated before about the properties of folding schemes. Now, it turns out that this is sufficient to recover a folding scheme for polynomial relations. And now, by applying an incremental SNARK, in particular, proof carrying data implemented with our particular folding scheme, we'll be able to obtain the Mangrove SNARK. But all is fine and dandy. Sure, we recover a SNARK, but how does it actually perform concretely? Well, we can discuss a couple of performance metrics. In particular, this is estimated performance. So basically, I just constructed circuits for the the subcircuits of this repetitive circuit, and just recorded the costs of proving these individual subcircuits. For the Mangrove prover, in particular, with estimates from a MacBook Pro, for 2 to the 24 constraints, the Mangrove prover will take 2 minutes and under 400 megabytes of memory, while for 2 to the 32 constraints, it will take 8 hours and under 800 megabytes of memory. Now, this is all fine and dandy independently. How do we know whether this is concretely fast or slow? Well, it turns out that this is actually an improvement on existing monolithic SNARKs. In particular, we actually improve the proving costs for circuits that the Spartan prover can actually prove. Now, it's a little bit hard to do these sort of comparisons because when considering circuits of incredible size, most monolithic SNARKs just simply run out of memory. So we simply just can't benchmark according to those sizes. But there does exist one monolithic SNARK, which is a streaming prover with low memory. However, it's sort of an apples to oranges comparison. In particular, Gemini requires trusted setup, but also a structured reference string of linear size. So if you had a 2 to the 50 size circuit, you would also need a corresponding 2 to the 50 size structured reference string. But this will just provide a sort of comparison between our prover. So Gemini, running on a EC2 large instance, for 2 to the 24 constraints, will take 19 minutes and 1.2 gigabytes of memory, while for 2 to the 32 constraints, it'll take over 80 hours with 1.35 gigabytes of memory. So even when comparing to other existing streaming SNARKs, the Mangrove prover already has an order of magnitude improvement in terms of proving speed. But alas, how do our proof sizes compare? Well, if you take a look at our uncompressed proof sizes, they'll actually be incredibly large, but it's okay. Using similar techniques to the original NOVA paper, we'll just be able to compress the proof size using an existing transparent SNARK, consider Spartan. You may similarly use a non-transparent SNARK, sort of like Planck and Marlin, to also compress, but here we wanted to keep the sort of transparency requirements, so we used Spartan to sort of compress the proofs. And so we end up looking at like around 13 to 14K kilobytes in terms of the proof size. So the key takeaways of our construction is that we designed a uniformizing compiler, which is able to reduce the task of proving an arbitrary circuit to a sequence of identical steps. By really treating these identical steps as a member of a polynomial relation, we'll actually be able to avoid the expensive cost of committing within these recursive circuits. And finally, we designed a folding scheme for polynomial relations, which we can readily apply an incremental SNARK to obtain our overall Mangrove SNARK. And that's my presentation. However, there will be updates soon. In particular, we do not discuss the generalizations of accumulation without homomorphism and protostar currently in the version of the paper. Additionally, the benchmarks are with respect to a more inefficient, concretely, but asymptotically more efficient folding scheme. In particular, we actually construct a tree sort of folding scheme in the original paper. However, my belief is that by incorporating the sort of generalization of proto-galaxy and accumulation without homomorphism, we'll actually be able to obtain a even more concretely efficient prover. In particular, we'll have to perform half the number of group operations. And so my prediction is that the subcircuits will end up being a lot smaller, and so we'll have improved memory performance as well as concrete proving performance. So look out for updates soon. Cool. And that's my talk.
Thanks, Wilson, for this presentation. It was great. I need to dive much more in your paper, I have to confess, and I will do so because I'm really interested about your polynomial folding scheme. I had a couple of questions, if you don't mind. Some might not be exactly about folding, but I think they're interested. So a first question I have is, I don't know if you've read Raman Pasta. It's a folding paper that's quite recent. They introduce the notion of conditional folding, and they do so to be able to remove the ROM from the verification from the decision step. I don't know if you had a look at this paper. It's
so
quite
I did, yeah. So I did try to look at the paper. So they do target. The first thing is they target a different setting, so it's a little bit hard to compare. But it'd be interesting to see. So I think by removing the random oracle outside of like the folding step, they actually require an additional argument to somehow, perform these random oracle calls outside. And so I think they end up not recovering a succinct argument in terms of the number of random oracles, but I could be mistaken. The paper is quite dense, so it's a little hard to read thoroughly. So I'm not sure what they ultimately recover.
I thought it was quite interesting, and so I was wondering if you thought that conditional folding could be applied more general in more schemes, including yours or not. But I agree with you. The paper is quite dense, so it's not an easy question.
Yes, because I believe at the end they state that they somehow use some other existing works to obtain like to obtain succinctness, but I'm not sure if this means proof succinctness or verification succinctness. Because when you remove the random oracles outside of these arguments, you'll have to actually perform the random oracle call somewhere, right? And if you do a recursive proof system or folding to do these random oracle calls, then indeed you're doing folding anyways. And so somehow these random oracle calls have to be instantiated. So I'm not totally sure, but I think it'll take some more time to digest the work.
Thanks a lot. So the question that is a bit tangent to folding is because I worked a bit on it a while ago. In your first third of your presentation, you were talking about the difficulty of having so many commitments. I think it was just slide 19 when talking about your universal compiler. Yeah.
Slide. Sorry.
19, 20. Yeah. About here.
Oh, sorry. Give me what? There's a lot of animations. Okay, here. Yes. Yeah. So okay,
here. Yeah. So it's not folding, but it's aggregation, which is not so. There is a small intersection between the two. So if you don't know, it's not a problem. A few years ago, there was a paper called SNARK, which was looking at accumulation, and so we treated this problem of commitments by using basically some check protocols to aggregate different instances of the same proof system. So I was wondering if here we could do something similar. Of course, it wouldn't be on different instances, but on different chunks. And so, yeah.
Wait, so are you saying that
So
wait,
instead
sorry,
of doing, yeah, so instead of doing folding from now on, because you want to reduce the number of commitments, I could see potentially another thing we could do, which would be not folding but aggregation on the chunks by using techniques such as SNARK. It would still be quite expensive because in SNARK you are using commitments of commitments. You're using basically
Oh, I know what you're referring to. You're referring to like the it's like the doubly homomorphic commitments or something where it's like
yeah.
you do it's like pairing based, right?
Yes, that's what I was
Yes.
going to. So it's quite expensive because you're going to have to handle GT elements. But I thought that this could be a good avenue to look at if you're interested in aggregation.
Yeah, so the thing is though, in order to gain a benefit for this, so what's nice, right, is that in this sort of description of this current inefficient SNARK, each subcircuit can be evaluated independently of the other ones. And so when you start aggregating the cost of commitments, you'll have just one commitment being a commitment to like multiple sort of subchunks. And so then you sort of like what's nice, right, is that the memory requirement can just be, the least number of these sort of subcircuits that you have to keep in memory.
Mhm.
That's one comment. Another comment is that when you operate over these pairing, using a pairing-based commitment scheme, you have to operate over a cycle of curves, which is pairing friendly. So that also introduces an overhead in terms of the size of the fields, but also the group elements. And in addition, it's not just the task of sort of proving that this commitment operation is satisfied, but also the corresponding polynomial F check. And so what's interesting is that in the ultimate circuit that we recover, so I'm just going to go here. What's interesting is that in the ultimate circuit we recover, you won't actually have to prove the execution of the function within the sort of recursive circuit itself. This is sort of handled inductively by the folding
Yeah.
scheme. And so it's I think like being able to maintain sort of pairing friendly pairing friendly free fields, for example, like the pasta cycle, but also like being able to handle each subcircuit independently is a sort of nice aspect. And so
Definitely.
what's kind of interesting is that this recursive subcircuit actually ends up being independent of the chunk size. And so you can sort of scale the chunk sizes also similarly without actually affecting the overall recursive cost.
Yeah. Yeah, that would have been my last question about the chunking strategy, but I guess the smaller chunks you have, the more efficiency you get, but you would have to consider. I'm not sure how you would tweak the security parameters to increase the depth of your recursion.
Oh, sorry, the depth. So yes. So currently, in order to be actually knowledge sound for polynomial length extended witness vectors, you'll always have to have the recursion depth, in particular the depth of this repetitive circuit to be constant.
Yeah.
And so in order to have a constant depth, you'll actually have to have an arity of the recursive circuit, particularly if you view the circuit as a tree, to be linear in the security parameter. And so that can also, and then what people consider to be linear in the security parameter is also a matter of like sort of, concrete preference.
Yes.
But in particular, this sort of, sorry, let me get to it. This sort of arity. So here we included the tree arity as this sort of member K. What's interesting is that the arity doesn't actually completely affect the proving performance that much. It's because it ends up being that the cost of representing the group elements for these sort of recursive circuits ends up being like pretty large in terms of like a constant overhead. And so minimizing these things will actually create a more gap between different arities. But what different arities provide is they provide better parallelism. In particular, if your arity is 32, then you can actually just have 32 independent subprocessors, just like computing the SNARK. And
Yeah.
so the trade-off with arity is that sure, you get a higher memory requirement because each like recursive subcircuit has to handle like a folding of like 32 instances, for example. But you get more parallelism. So there's like a sort of trade-off factor. But what's interesting is that the sort of first order impact, sorry, the thing that like affects the proving performance the most is simply just the size of each chunk. Because each chunks, sorry, I say it, the less chunks you have overall, particularly the greater the size of the chunk, the smaller the overall recursive tree will end up being. Like it's like a direct order of magnitude smaller. And so larger chunks, the more efficient, so you'll be able to recover a more efficient SNARK, but then the proof sizes are larger because we did this sort of folding scheme. But then you can always apply the Spartan compression. And so the gap between these proof sizes is not so large. So it seems like the best strategy is just to have a very large chunk size and then just choose the corresponding arity parameter that matches your best setup.
Thanks a lot. We have a question from the audience. What implications do you think Mangrove has for ZKML and privacy preserving machine learning tasks?
Oh, sorry, give me one moment here.
Sure.
Trying to see the chat. Okay, so what implications do you think that Mangrove will have for ZKML and privacy preserving machine learning tasks? Well, I guess it depends on what type of circuits you're considering to prove in ZKML. In particular, if you have a very, very large, I don't know, like matrix multiplication or a very, very large overall circuit for, I don't know, proving that you've trained over some committed data, then you can just use Mangrove to prove this computation in a way in which you can actually have lower memory requirements. And so I am not sure what the overheads are for ZKML, but in general, if you have some very large circuit that you can't keep in memory, then this will allow you to do so.
Yeah, in my experience, memory is the next difficulty with proving time. I'm part of the ZK-EVM project, and we have a circuit of size 2 to the 26.8, something in this order of magnitude. And I think we are using 10 terabytes of RAM. So it is there is no optimization at the moment, but it is.
Oh, wow.
Yes. So you are order of magnitude lower than that. So it is quite interesting. Proof size, as you've shown, and as research has shown the past few years, is not so important because you can always add an extra SNARK on top of it to compress your proofs. And proving time, more and more people are releasing linear proving time, and I think that's the best we can reach. So yeah, memory I think is the next dimension that people should be looking at, and that's why this paper is so interesting right now.
Yeah, I think there's tons of improvements that can be made to the existing like sort of benchmarks of Mangrove. In particular, I just sort of generalize what we had in the revisiting Nova paper, in particular, where we just cycle between the two curves. And so I believe you guys recently implemented CycleFold. And so with CycleFold and also with sort of the generalization of proto-galaxy that we consider, I believe Mangrove can actually be very, very competitive. In particular, by doing this sort of cycle, we also introduce more memory overhead, right? Because you have to represent accumulators of, or I guess some people call them accumulators, some people call them committed instances, right? Of the curve one over curve and also curve two. So we have to sort of carry that up the proving tree. But if we use CycleFold, we'll be able to actually minimize probably overall circuit size. Also, what's sort of killing us is that in the current benchmark, we use tree folding. And so we have to pay for the random oracle calls as well as the sort of all the levels of this sort of folding tree. Well, proto-galaxy is just a single round. So I do think that there's actually going to be a pretty big improvement in performance, but updates soon. So we have to sort of try out these benchmarks.
Yeah, we'll
so
be looking forward to it.
Sorry.
Oh, I was just saying we'll be definitely looking forward to it.
Yes. Yeah. So, oh man, I feel like someday, hopefully, we'll be able to prove circuits of very, very, very large size. Like I'm kind of impressed that a 2 to the 26 or two, oh, I guess it makes sense. Those are very, very large numbers. And so monolithic SNARKs don't immediately like scale very, very well. So the terabytes is kind of understandable.
Yeah, it's a very large unoptimized circuits for ZKVM. So we have hundreds of columns, selectors. So it is the ZKVM projects are monstrosity for SNARKs. So it is a special case.
Oh, yeah. So here I presented the case in which we just have one selector vector. But
Yeah.
of course, you can just imagine that the chunks are merely just chunks of the multiple selector vectors, and then the gate polynomial just takes in each of the selector vectors.
Yeah.
In particular, so here it's just we presented just in our paper the simplest version of Planck generalization, but of course you can immediately generalize if you have like more columns. And so it seems like it's almost readily just like any system that uses sort of Planck generalization, it seems almost like readily like fitting. So it's quite close.
Yeah. So I don't see any other questions in the chat. So thanks a lot for coming, Wilson. We're really happy to have you today. We'll be looking forward to your dates and your next papers.
Cool.
And thanks for the audience for being here. Have a good day
Yeah.
or evening.
Thank you for inviting me. Okay. Catch all.